In this video, we'll graph a few sets of parametric equations. Our first set is x equals t and y equals 2t minus 1. And to graph this, we could just make a table of values. So at time t, what are the coordinates x and y? Because these coordinates of x and y are defined by t, not on each other, but just on t. So let's assume that we can go backwards in time, or if t is sometimes not a time parameter, a parametric equation is not always based on time. Oftentimes it is, but it's not always. So let's say we can go backwards at -2, -1, and then up to 0, and then 1, 2, 3. Now what are the corresponding x and y coordinates? Well, let's see. X is exactly whatever t is. So x would be -2, -1, 0, 1, 2, and 3. Y is defined by 2t minus 1. So we're going to say for the first one, if t is -2, then we've got 2 times -2 minus 1, and that gives us -5. And we can go right down the line, filling in the appropriate y values. -1, 1, 3, 5. Now what we have are a set of ordered pairs. All of these ordered pairs can be plotted on this Cartesian coordinate plane over here, and then we can sketch a graph through these. So let's plot these. -2, -5, that brings us down here, and -1, -3 is here, and 0, -1 is here, up 1, 0, -1 is here, 1, 1 is right here, 2, 3 is here, and 3, 5 is here. Sketching through that shows that this is actually a linear graph. Those dots exactly line up. And we also have another thing that is interesting about this. Anytime you see x equals t as part of the parametric equations, you could have just rewritten this as y equals 2x minus 1. You could just plug in x instead of t in for that y component of the parametric equation. Now it won't always be linear, right? Think of the example of y equals 4x squared plus 18. That wouldn't be linear, but you could then still plug in x for the t. Now, this next example is not so easily defined as just plugging in x wherever you see t. You could, of course, solve this and convert this into a Cartesian form of just x and y, but we're going to leave it in terms of t. We're also going to think of this in strictly terms of time, where we will not go back in time. It'll just be time equals 0 and then on, because this is actually a set of parametric equations defining the motion of a projectile, perhaps a ball being thrown horizontally from 50 feet high. So we will make a table again with the t values and then some x and y coordinates, the corresponding coordinates. So let's start again at t 0, right? We won't go back in time on this one. And then t is 1 or 2, 3. I'm going to leave a space because something interesting is going to happen in between 3 and 4. And then I've got x equals, well, x is 60 times whatever t is. So it starts at 0 and then 60, 120, 180. We've got multiples of 60 you see here, and then 240. Y is this longer version, 50 minus 4.9 t squared. So I can fill in when t is 0. That's an easy one. We can do that in our head. That's just 50. The next one you might the next one isn't too bad in your head, but as they go on, it's easier with a calculator. I'll just fill these in. We've got 45.1. We have 30.4. We have 5.9. Then we have -28.4. I'm going to fill in this empty space here in just a minute. Well, here's what's happening. The projectile is starting at 50 feet high. So how are we going to define this? The x and y scales are not going to be the same in this. So let's go by tens here. 10, 20, 30, 40, 50. So this is our 50 here. And the x coordinates are going to have to be scaled much larger because you can see x is much bigger here. So let's say every 4 is 100, or every 1 unit represents 25. So this is 100, and 25, 50, 75. Here's 200. So it gives it a nice scaling of what's going on. This is 0 right here. Okay, so this ball is being thrown. Let's say this ball is being thrown, and let me really give some nice axes here. And at time t equals 0, we have x is 0. The ball has gone nowhere in the x direction yet. But at time t equals 1, x is at 60, which is about here, right along this line. The y value has dropped. So the gravity is acting on this ball, and it's dropping down to about 45.1. Remember, each of these vertical lines is worth 10 in the vertical scale, the y scale. So we've got a coordinate of 60, 45.1, and that lands us about here. Then we have 120, 30.4. That's about here. And then we have 180, 5.9. 180 would be right about here, and then 5.9 is way down here. And then we've got something interesting, 240, negative 28.4. That's way down here. Well, what's going on? This ball is tracing a path just as you would expect it to, and that is it's falling. It's going out horizontally, so it does go in this direction, but it falls as it does so. Well, what we're interested in then is, well, what happens? When does it hit the ground? When is the y coordinate 0? At what time t is the y coordinate 0? Well, doing some algebra, you can just say 0 equals 50 minus 4.9 t squared, and then solve for t, and you get a 3.19. 3.19. Say this is all in feet per second. So 3.19 seconds. Then the x coordinate would be, corresponding x would be 192. So after 3.19 seconds, the ball has traveled 192 feet right here, and it has finally reached the ground. So there's an example of a couple of very different parametric equations. However, we could graph them using the same method.